An open neutral on the load side can indeed be the problem even when measuring voltage at the house sub-panel. This scenario occurs if the neutral connection between the service panel and the sub-panel is compromised. When this happens, the neutral wire loses its connection to the grounding system at the sub-panel. This disconnection causes the voltage to increase on one phase and decrease on the other, resulting in a voltage imbalance. Several other conditions can mimic the symptoms of an open neutral. Firstly, a faulty transformer can introduce imbalances in voltage levels between phases. If the transformer windings are damaged or not functioning correctly, it can lead to uneven voltage distribution. Secondly, a loose connection within the circuit creates high resistance. This increased resistance can cause significant voltage drops, affecting the voltage balance across different phases. Thirdly, overloading one phase can also lead to voltage drops. When one phase carries excessive current, its voltage decreases relative to the other phases, leading to an imbalance. Fourthly, inductive and capacitive loads can cause voltage distortions. Inductive loads, such as motors, and capacitive loads, such as capacitors, can alter voltage waveforms, resulting in imbalances. Fifthly, an unbalanced three-phase system will have uneven voltage levels on the different phases. This is due to unequal load distribution across the phases. To effectively troubleshoot a voltage imbalance, consider these steps. 1. Check neutral connections by carefully inspecting them at the service panel, sub-panel, and all intermediate junction boxes along the circuit. Ensure that all connections are secure and free from corrosion. 2. Measure voltage at multiple points along the circuit. Use a voltmeter to measure the voltage between phases and neutral at various locations, including the service panel, sub-panel, and suspect devices. This will help you pinpoint where the voltage imbalance begins. 3. Disconnect loads systematically and observe the voltage levels. If the voltage imbalance disappears when certain loads are disconnected, this indicates a faulty device or overloading on that particular circuit. 4. Check the transformer for any signs of damage or loose connections. Measure the voltage across both the primary and secondary windings to ensure they are within the expected range. If all other possibilities have been ruled out, contact the utility company. They can assess the voltage at the utility pole and identify any potential issues on their end. Measuring voltage accurately is crucial in electrical troubleshooting. Firstly, always use a calibrated digital multimeter. These meters provide accurate and reliable voltage readings. Secondly, ensure the meter is set to the correct voltage range, either alternating current volts or direct current volts, depending on the circuit you are testing. Thirdly, when measuring voltage, connect the meter probes in parallel with the circuit. Place the red probe on the point where you want to measure the voltage and the black probe on the neutral or ground reference. Fourthly, take multiple readings at different points in the circuit to identify any voltage drops or imbalances. Fifthly, be aware of ghost voltages which can appear when measuring circuits with high impedance. These phantom voltages are typically very low current and do not indicate a real voltage issue. When troubleshooting voltage drops, several factors can contribute to the problem. Firstly, undersized wiring can cause significant voltage drops, especially over long distances. Consult the National Electrical Code, NEC, Table 310.15b16 to ensure that the wire size is appropriate for the current and distance. Secondly, loose connections or corroded terminals increase resistance, leading to voltage drops. Inspect and tighten all connections to ensure they are secure and clean. Thirdly, excessive load on a circuit can cause voltage drops. Distribute the load evenly across different circuits to prevent overloading any single circuit. Fourthly, long circuit runs will have more resistance and therefore more voltage drop. Consider using larger gauge wire for long runs to minimize voltage drop. Fifthly, branch circuits should be designed to minimize voltage drop. The NEC recommends a maximum voltage drop of 3% in branch circuits and 5% overall, including the feeder. Understanding transformer connections is essential for diagnosing voltage issues. Firstly, transformers are used to step up or step down voltage levels. The primary winding is connected to the source voltage, and the secondary winding provides the output voltage. Secondly, Different transformer configurations, such as delta and Y, affect the voltage and current characteristics of the system. A delta connection has a higher phase-to-phase voltage, while a Y connection has a neutral point. Thirdly, when connecting transformers in parallel, ensure they have the same voltage ratio, impedance, and phase angle. This prevents circulating currents between the transformers. Fourthly, three-phase transformers can be connected in various configurations, such as delta-delta, delta-Y, Y-delta, and Y-Y. Each configuration has unique voltage and current characteristics that must be considered for proper operation. Fifthly, auto transformers use a single winding for both the primary and secondary circuits. They are typically used for small voltage adjustments and are more efficient than traditional transformers for similar applications. Grounding systems play a crucial role in electrical safety and voltage stability. Firstly, the grounding system provides a low impedance path for fault currents to return to the source, allowing overcurrent protective devices to trip and clear the fault. Secondly, the grounding electrode system, consisting of ground rods, metal water pipes, or concrete encased electrodes, connects the electrical system to the earth. This provides a stable reference point for voltage. Thirdly, the equipment grounding conductor connects the metal enclosures of electrical equipment to the grounding system. This ensures that any fault current will safely return to the source. Fourthly, the neutral conductor is grounded at the service entrance. This provides a return path for unbalanced currents in a three-phase system. Fifthly, ground fault circuit interrupters, GFCIs, protect people from electric shock by detecting small imbalances in current. They quickly trip the circuit when a ground fault is detected. Electrical meters are essential tools for measuring voltage, current, and resistance. Firstly, voltmeters measure the potential difference between 2 points in a circuit. They are connected in parallel with the circuit. Secondly, ammeters measure the current flowing through a circuit. They are connected in series with the circuit. Thirdly, ohmmeters measure the resistance of a component or circuit. The circuit must be de-energized before measuring resistance. Fourthly, clamp-on ammeters measure current without breaking the circuit. They use a magnetic field to determine the current flow. Fifthly, power quality analyzers measure voltage, current, harmonics, and other parameters to assess the overall quality of electrical power. Understanding circuit breakers and fuses is critical for overcurrent protection. Firstly, circuit breakers are resettable devices that trip when the current exceeds their rated value. They protect circuits from overloads and short circuits. Secondly, fuses are one-time devices that melt and break the circuit when the current exceeds their rated value. They also provide overcurrent protection. Thirdly, time delay fuses allow temporary overloads, such as motor starting currents, without tripping. They provide better protection for motor circuits. Fourthly, circuit breakers have different trip characteristics, such as thermomagnetic and electronic. Thermomagnetic breakers use heat and magnetism to trip, while electronic breakers use electronic sensors. Fifthly, ground fault circuit breakers, GFCBs, protect against ground faults in addition to overcurrents. They trip when a small current leakage to ground is detected. Voltage regulation ensures that the voltage remains within acceptable limits under varying load conditions. Firstly, voltage regulators are used to maintain a constant output voltage despite changes in input voltage or load current. Secondly, automatic voltage regulators, AVRs, are used in generators and other power equipment to maintain a stable voltage output. Thirdly, tap-changing transformers adjust the voltage ratio to compensate for voltage fluctuations. They are commonly used in power distribution systems. Fourthly, static power compensators, SVCs, provide reactive power support to stabilize voltage levels. They are used in transmission and distribution networks. Fifthly, power factor correction capacitors improve the power factor and reduce voltage drop. They are commonly used in industrial facilities. Harmonics can cause voltage distortions and equipment malfunctions. Firstly, harmonics are multiples of the fundamental frequency, such as the third, fifth, and seventh harmonics. Secondly, nonlinear loads, such as electronic devices and switching power supplies, generate harmonics. Thirdly, harmonics can cause overheating of transformers, motors, and other equipment. Fourthly, harmonic filters are used to reduce harmonic distortion. They typically consist of tuned circuits that block specific harmonic frequencies. Fifthly, total harmonic distortion (THD) is a measure of the amount of harmonic content in a voltage or current waveform. A high THD indicates significant harmonic distortion. Power factor correction improves the efficiency of electrical systems. Firstly, power factor is the ratio of real power to apparent power. A low power factor indicates that a large portion of the current is reactive. Secondly, inductive loads, such as motors, have a lagging power factor. Capacitive loads have a leading power factor. Thirdly, power factor correction capacitors are used to improve the power factor by providing reactive power. Fourthly, improving the power factor reduces current flow, voltage drop, and energy losses. Fifthly, utilities often charge penalties for low power factors. NEC Article 250 covers grounding and bonding requirements. Firstly, the purpose of grounding is to provide a low impedance path for fault currents to return to the source. Secondly, the grounding electrode system connects the electrical system to the earth. Thirdly, the equipment grounding conductor connects the metal enclosures of the electrical equipment to the grounding system. Fourthly, bonding ensures that all metal parts are electrically connected to create a low impedance path for fault currents. Fifthly, ground fault circuit interrupters, GFCIs, protect people from electric shock by detecting small imbalances in current. NEC Article 310 covers conductor requirements for ampacity and sizing. Firstly, ampacity is the maximum current a conductor can carry continuously without exceeding its temperature rating. Secondly, conductor ampacity is affected by factors such as ambient temperature, number of conductors in a raceway, and insulation type. Thirdly, NEC Table 310.15b16 provides ampacity ratings for various conductor sizes and insulation types. Fourthly, voltage drop must be considered when sizing conductors for long runs. Fifthly, conductors must be protected by overcurrent protective devices such as circuit breakers and fuses. NEC Article 408 covers switchboards and panel boards. Firstly, switchboards and panel boards are used to distribute power to various circuits. Secondly, they must be properly rated for the voltage and current they will carry. Thirdly, overcurrent protective devices must be provided for each circuit. Fourthly, switchboards and panel boards must be accessible and properly labeled. Fifthly, the neutral bus must be properly grounded and bonded. Always de-energize circuits before working on them. Use a voltmeter to verify that the circuit is de-energized. Wear appropriate personal protective equipment (PPE) such as safety glasses, gloves, and insulated tools. Follow lockout-tagout procedures to prevent accidental re-energization of the circuit. Be aware of the potential hazards of working with electricity such as electric shock, arc flash, and arc blast. Consult the NEC and other applicable codes and standards for safe electrical practices. Always consult with a qualified electrician for complex electrical troubleshooting and repairs. Maintaining a log of all electrical work performed can help with future troubleshooting. Include details such as the date, time, description of work, and any issues encountered. Regularly inspect electrical equipment for signs of wear and tear, such as loose connections, damaged insulation, and corrosion. Addressing these issues promptly can prevent more serious problems from developing. Periodically test ground fault circuit interrupters, GFCIs, to ensure they are functioning properly. Replace any GFCIs that fail to trip when tested. Use surge protectors to protect sensitive electronic equipment from voltage spikes and surges. Surge protectors divert excess voltage to ground, preventing damage to equipment. Consider using a power conditioner to filter out noise and voltage fluctuations. Power conditioners provide clean and stable power to sensitive electronic equipment. When installing new electrical equipment, follow the manufacturer's instructions and all applicable codes and standards. Ensure that the equipment is properly grounded and protected by overcurrent protective devices. Use a thermal imager to detect hot spots in electrical equipment. Hotspots can indicate loose connections, overloaded circuits, or other problems. Conduct regular infrared scans of electrical equipment to identify potential issues before they lead to failures. Implementing a preventive maintenance program can help extend the life of electrical equipment and prevent costly downtime. A well-designed and maintained electrical system is essential for safety, reliability, and efficiency. By understanding the principles of electrical troubleshooting and following safe work practices, you can effectively diagnose and resolve electrical problems. This will help ensure the safe and reliable operation of electrical equipment and systems. Remember to always prioritize safety and consult with a qualified electrician when needed. Proper grounding is critical for electrical safety. Ensure all electrical equipment is properly grounded according to the NEC. Grounding provides a path for fault current to flow back to the source, tripping the circuit breaker or fuse and preventing electrical shock. Regularly inspect grounding connections to ensure they are tight and free from corrosion. Use appropriate grounding techniques for different types of equipment and installations. Bonding is also essential for electrical safety. Bond all metal parts of electrical equipment together to create a low impedance path for fault current. Bonding helps to equalize potential and prevent electrical shock. Use appropriate bonding techniques for different types of equipment and installations. Overcurrent protection devices, such as circuit breakers and fuses, protect electrical circuits from overloads and short circuits. Select the appropriate overcurrent protection device for each circuit based on the conductor ampacity and the load requirements. Ensure that overcurrent protection devices are properly sized and installed according to the NEC. Regularly inspect overcurrent protection devices to ensure they are functioning properly. Voltage drop is a common problem in electrical circuits, especially in long runs. Excessive voltage drop can cause equipment to malfunction or fail. Size conductors appropriately to minimize voltage drop. Consider using larger conductors for long runs. Calculate voltage drop using the appropriate formulas and NEC tables. Harmonics can cause problems in electrical systems, such as overheating, voltage distortion, and equipment malfunction. Minimize harmonics by using linear loads and avoiding nonlinear loads. Use harmonic filters to reduce harmonic distortion. Monitor harmonic levels to ensure they are within acceptable limits. Power factor is a measure of how efficiently electrical power is used. A low power factor can cause increased current flow, voltage drop, and energy losses. Improve power factor by using power factor correction capacitors. Monitor power factor to ensure it is within acceptable limits. Electrical safety is paramount. Always follow safe work practices when working with electricity. De-energize circuits before working on them. Use appropriate personal protective equipment, PPE, such as safety glasses, gloves, and insulated tools. Follow lockout-tagout procedures to prevent accidental re-energization of the circuit. Be aware of the potential hazards of working with electricity, such as electric shock, arc flash, and arc blast. Consult the NEC and other applicable codes and standards for safe electrical practices. Regularly inspect electrical equipment and systems for potential hazards. Address any hazards promptly to prevent accidents. Provide electrical safety training to all employees who work with or around electricity. Foster a culture of safety in the workplace. By following these guidelines, you can create a safe and reliable electrical system.